Welcome to our part 2 of our solar troubleshooting series. In this part we're going to be talking about visual inspections and troubleshooting. Remember, in part 1 we discussed the various types of systems, the inverters and some of the components. We did discuss degradation and lifespan. We looked at some monitoring. We looked at some of the ground versus roof mounted arrays. In this part we're going to look at the visual inspection of the overall system, visual inspection of panels, visual inspection of wiring, and visual inspection of safety components. We do the visual inspections first. This is so you know what the system looks like, where the components are, and the overall conditions before you start any electrical troubleshooting. Do not come to any conclusions or recommend any repairs based on your visual troubleshooting. This is still information gathering, so then you can dig in deeper. The first thing you need to do is find and observe the utility feeds. Is it above ground, underground? What's the condition? Where's the meter? Find the distribution panel, people know it as a breaker panel, and find the breakers for the solar array if there are any. Sometimes solar systems are tied directly into the main power feed at the meter box. Be careful. Know where your disconnects and your breakers are. Find all the disconnects on the AC side of the solar system. Check and make sure they're fused. I don't want you to test anything yet. This is still visual only. You haven't even taken a tool out of your tool bag yet. So, electrical location on the side of a house. Okay, you can see it all there. There's disconnects, there's transfer switches, there's meters, there's solar disconnects. Okay, then you're going to find the inverters or the connection box. Okay, if you have a single inverter or two if a larger system, you know you have a string-based system. If it's a consolidation box or collector box, you have a microinverter system. People call this box different things. Some people call it a communication box as well. Find all the data plates and look at the information, record it. It's important. You need to know what the wattage input is from the DC side. You need to know the wattage output on the AC side. You need to know the voltage output on the AC side, and you need to know the max voltage and current on the DC side. Then you need to figure out the age of the system that you can look at. Normally you can figure it out through the serial numbers. You cannot do your electrical troubleshooting, which is in our next part, without this information. Again, this is important information. Okay, I can look at this data plate. I can see that the system was manufactured in 2013. Okay, my model number tells me a lot. If I look this up on the web or even look at what it is, it's a 5 kilowatt system, 5,000 watts per hour. Okay, max continuous output and max reduced output. Okay, this is my output power between 5 and 3,000. Okay, then I can go here further and I can say the input operating voltage has to be between 175 and 480 volts DC, and that's per inverter. There's microinverters in here, so that this actually has 3 of them. So each one of them can have that number in there. Okay, and then I have 2 times 15 amps DC. So my max string amperage can be 15 amps. Okay, and also gives operating temperatures and stuff like that there. Don't normally have to worry about those. But that data plate gives you a lot of good information. You're going to continue looking at your visual inspection points. See, here again, I have an inverter, so I know it's a string system. Second inverter, I know it's a string system. Okay, this inverter has an extra outlet at the bottom of it. Believe it or not, if power goes out, you can flick the switch on and you can still use just that outlet and not lose your islanding capability. Grid tied with battery, locate the transfer switch, locate the battery pack, and if possible, open it to get a number of batteries and look at the condition of these batteries. This is an example of a transfer switch and a battery rack. This battery rack has 6 batteries in it, and it's relatively new. It's in good condition. Here's my transfer switch. Main power cutoff to the entire building. Then there's a set of relays and solenoids here to transfer over to the islanded system in case of power failure. Disconnects the line from the utility and puts it totally on to the inverter and the batteries. The battery pack also has data. Max battery current is 35 amps. Well, I have 6 of them. So that tells me what my current can be. Okay? And there's more there. So the next thing I'm going to do is the panel inspection. But I do want to make a note on safety before you approach the panels. For ground-mounted panels, watch for nails and uninsulated wiring. If it's a metal rack system, do not touch that rack without testing for voltage first. If it's a string inverter, you're going to have DC voltage present. If it's microinverters, check for both AC and DC voltage. Check for wasps, bees, and hornets' nest. You'll find them occasionally. Okay? The reason we want to check for voltage on metal rack systems is that some of the rodents, such as squirrels and mice, love chewing the insulation off wires. And that rack could be energized with, let's say, positive, and you don't know it is. So always check for voltage first. For roof-mounted panels, keep ladder safety in mind. Follow OSHA rules on this. Do not walk on clay tile roofs without safety gear. Be very careful on metal roofs as well. Metal roofs can get energized if they're not properly grounded. Do not walk on wet, ice, or snow-covered roofs. Be careful grabbing onto mounting rails and leaning on any component of the system. Be very careful of any roof-mounted exposed wiring. Look for bees, wasps, birds, bats, and squirrels. A surprise on a roof could be deadly. If it's unsafe, find another method to look at these panels. You want to first count the number of panels in every location. If there's different arrays, make sure you look at the different arrays. But get an idea of the number of panels, because you're going to need this later in your electrical inspection. Look at the damage. Look for any panels that are damaged. What type of damage? Is it major cracking? Is it bending? Is it frame damage? Are there holes in the panels, or is there just micro cracks? Are the frames bent and broken? What does the mounting look like? Are the rail connections tight and in good shape, or is things loose? Try lifting a few panels. Okay, again, don't touch without checking for voltage first, but try lifting a panel or two and see if they lift or rattle or wiggle the entire array. What do they look like? What do they feel like? Look for cracked panels. The one on the left is seriously cracked. Okay, it's actually bent a little bit. You can't see it in the picture. The one on the right has a lot of micro cracks, but believe it or not, it actually still provides full power. Is it pretty? No. Is it damaged? Yes. But it is providing full power. Okay, so look for the damages. Perfect. Here's an example of the left one. There's no damage whatsoever on these solar panels that you can see. While I'm looking at panels, I'm looking at the wiring. Are any panels running exposed in a weather-tight conduit? What's the roof penetrations like? These are called sunny portals, where they actually, believe it or not, this is where the rooftop wiring plugs in and connects to wiring in the attic that goes down into the inverter. So what does your rooftop wiring look like? If you look closely at this picture here, you can see the rails that things are mounted on. Okay, the rail connections. There's 3 rails on every panel, top, middle, and bottom. You can look closer here and you can see, look across. Cracks and holes show up very well when you look across and take sort of a side view. You can also see under the panels. I could see more wiring here. I could see another sunny portal here, another roof connection, and again the one we looked at earlier. You can see where the rails are mounted. There's flashing. Okay, the shingles must come down over the flashing at the top, and the flashing is over the shingles at the bottom. Any other method of this, and water's going to get in underneath the shingles. This is just another set of panels that want to look at, another location, again looking across here, there's no visual damage to these panels. There's an old hydro water heater panel here. This is for a domestic water heater tied into. We're not worried about that. I'm strictly worried about the solar panels in these pictures. Okay, they look level, they look clean, they're all facing one direction. Look under the panels. Are there any broken wiring, dangling connection boxes, microinverters not properly mounted, they're loose, they're hanging? Is there squirrel damage? Is there wiring that's broken? Or check and see if all the panels are wired in series. This is sort of important. Okay, how does the wiring come off the roof? Is it one set of DC? Is it just a single positive and negative? Or are there two sets coming off the roof or more? What's the condition of that wiring? Is there a ground wire connecting all panels and going off the roof to the inverter collector box? Panels have to be grounded. Okay, all the metal on panels have to be grounded. Okay, some dangling wire on these panels. Okay, there's one connector box here that has fallen off and it has sort of been remounted. There's another one there. Okay, there's a dangling wire here. So some of this is just worth noting. Does it affect operation? No. Could it in the future? Yes. So that's something you'd want to talk to your customer about to resolve. DC disconnects are important. Okay, you got to be able to disconnect the DC side of a system fast. Okay, now be aware you do not use these DC disconnects in day-to-day operation. This is emergency use only. If you pull a DC disconnect, you can expect that there will be a spark, unless the panels are shut off at the inverter first. You're looking for loose connections and wiring. Okay, this connector here, this white wire wasn't crimped in properly, and thus there was a problem with the panels. Okay, so we're looking for loose connections. We're looking for wire that doesn't make sense from a sizing perspective. I have heavy wire here, and I have very small wire coming in there as well. So there's a sizing issue. Looking at mounting, how are the panels mounted? This one, it's mounted, screwed into the metal frame of the panel and then into the wood. That's fine. We want to look at the panel data plates. You cannot troubleshoot solar without checking and recording the data plate information. You have to get panel output. You got to get the operational voltage, get the short circuit voltage, get the maximum circuit voltage, maximum circuit amperage, and the age we can figure out from the serial number most often. So you want the make, model, and serial number of the panel. Again, this is all important because of the next step of troubleshooting. If your system has multiple panel types or brands, capture it for each and try to get a number of panels that match each type. So here's two different data plates. Okay, one is Sanity Solar and one is just solar module. We don't know who made it. Okay. So again, we have a 255 watt panel here, 300 watt panel here. We have different amperages and voltages based on the type of the panel. The next step in the visual inspection is the use of thermal imaging. This portion is relatively new and is an addition since the last time I did a similar presentation. Thermal imaging can find hidden damages in solar panels. Damaged or failed cells will show in thermal imaging, cracks will show, and areas of overheating will show. You need to practice this method before relying on it. I would not, the first time you're out there with a thermal imaging camera, I would not use it to officially diagnose and make recommendations on panels. They need to go along with what you're seeing on other panels. Camera angles and cloud cover matters. You do not want more than 50% cloud cover when you're using thermal imaging. That's because we have to have enough solar radiation on the panels. You want to take the pictures between 5 and 60 degree angle. Not straight down and not directly sideways. Straight down, you're going to have yourself in the reflection. It's going to have the reflection of the sun. It's a useless picture. So again, between 5 and 60 degrees. So you hold your camera in the green area on the sort of on the diagram on the right. Okay, here's a couple examples. The non-damaged panel. The heat signature is sort of even, and heat is being radiated from the roof. You can see the panel. There's a little bit of heat signature under the left panel, and it's hard. Let me see if I can change my pen color. Probably not. Okay, but these are non-damaged panels. It's very even. The yellow off to the sides of the panel is just the heat being radiated back off the roof. In thermal imaging, the darker the color, the cooler the area. The lighter the color towards white, the hotter the area. The picture on the right, they're also non-damaged panel. There is a heat signature I was a little bit worried about right here. And I'll show on other panels why I was concerned about that. But a quick visual inspection under the panel showed an old mounting bracket that is showing a heat signature from the heat on the roof. So again, just because you see it in thermal imaging may not mean that there's a problem. You've got to look under the panels. Now, this is the left picture is a thermal image of a physically damaged panel. What we're looking for is the hot spots. The darker the color, the cooler the temperature difference. The lighter the color, the greater the temperature. Okay, I'm very concerned about two spots in this panel. You have a yellow area over on the left, and I'm not sure if you can see the pen I just used on it, but there's splotches, there's yellow, and it's uneven. That's a that's a broken area in the panel. Then I have a very large heat signature right there. Okay, and if you look closer, you can actually see some areas in that panel that's damaged as well. Damaged area and damaged cells in a panel will show up as heat. Okay, on the right here, these are visually non-damaged panels on the same array where the visually damaged ones were. Okay, they're electrically damaged as well. So they might have looked perfect to just you looking at them, but there's electrical issues in them. We're not worried about the large areas of heat, but you're worried about the small rectangular and square areas of heat. Okay, this is areas of the cells that are not working quite properly. There's some there, there's one there, there's one there. Okay, these are areas that are not producing power. Remember, solar panels are a whole bunch of solar cells put together. So your panel could still be good, but there's some degradation in output based on non-working individual cells. Okay, this is the one on the left is another panel with hidden electrical damage. You'll notice the squares of rectangular hot areas. These are damaged internal components. The cells are damaged here inside the panels. Okay. It's to different extents, but there's damage to the panels. Okay, the one on the right is an example of a non-damaged panel. The warm areas are relatively even. They're not in a geometrical shape, and they're not around any visual damage. There's that's heat from the roof. I can actually over here see collector box or a vent or something. There's a little bit of heating in a square there, but I know that's where the connector is into the solar cell, and there's a diode in that's going to heat up a little bit. So that's a non-damaged panel. Again, general good gradient of heat. When you use thermal imaging and find a possible issue, you still have to look closer to see if you can find the reason for the heat or lack of heat. Thermal imaging is a tool. It does not take the place of technical knowledge and systematic troubleshooting. So at this point, once you've gone through all the arrays and the panels, you know the type of system, you know the type of mounting, you know the number of panels, you know the inverter wattage and voltage for the DC and AC side. You know the panel output voltage and wattage. You know the panel age. You know the inverter age. And you know the condition of panels and wiring. And you know if there's any hidden damage by use of thermal imaging. The one thing I should note on the subject of inverters, if you're on a roof with a microinverter system, capture a couple of those data plates. And just be aware that there is a little bit of heat signature off the microinverters that will pop up. So look at your thermal imaging pictures and look at the heat signatures. You may pick up a few microinverters on those systems. Before we start the electrical inspection, do some basic calculations. Your system DC output is the panel wattage times the number of panels. That's my rated output from the panels. You want to also look at the array voltage. Panels wired in series times the rated output voltage. Remember, in a series circuit, voltage adds, amperage is the same. So the variable that drives the output of the system or of that array is the voltage. Then you can take a look at the expected output. It's the max rated panel amperage times cloud cover percentage. This is a very rough estimate, but cloud cover affects output. Compare the calculation to the specs. For a string inverter, compare your calculations to the rated DC of the inverter. For example, if I have 20 320 watt panels, this is a 6400 watt total output from the array. If there's an 8000 watt inverter, that inverter will never achieve 8000 watts. It's not possible. So again, let's do some basic troubleshooting without pulling our tools out. If the customer's complaining that we have an 8000 watt inverter, or they would know it as 8 kilowatts, and you only have 20 320 watt panels, this isn't doable. If there's 2200 watt panels and a 3800 watt inverter, the panels are above the inverter by 200 watts. This is frequently done and nothing to worry about. You'll make that 3800 watt inverter. Complete the visual inspection by repeating the sequence for all of the mounting locations. So if you're roof, you're doing it once for the roof, you're doing it for each of the side arrays, you're doing it for any ground mounted arrays. It helps if you use a checklist. Develop something that works for you. Do your calculations before taking out any electrical testing tool. That way you know what you're working with before you start testing. So in part 2, we've looked at all the parts of the visual inspection. Okay, hopefully some of the examples and pictures have helped. You want to make sure you keep safety in mind and don't jump to any conclusions based on visual inspection. You still have to do the electrical inspection. Okay, just a note on some of the photographs in this series, just because people have asked this question before. Most of these photos I used are taken on my own system for the purpose of these videos. For safety reasons, I did use some drone photography. I'm an FAA Part 107 certified commercial unmanned aircraft pilot. Property is in uncontrolled airspace. Do not use drone photography unless you are properly licensed and insured and your employer allows you to do so. Know your surroundings at all times. Again, my standard disclaimer I got to put in here. The opinions expressed in this presentation are my own and are not those of my employer. If I say something you disagree with, blame me, not my employer. And again, to repeat, this is not a presentation designed for the do-it-yourself owner. There are serious safety concerns when servicing a solar system. Only do so if you're properly trained in electrical and ladder safety.